Hi everyone, welcome to my channel. This video is going to cover the topic of BCD code, binary coded decimal. But before we get into that, let's define encoding. Encoding is when numbers, letters, or words are represented by a special group of symbols. This is called encoding. Now, when a decimal number is represented by its equivalent binary number, we call this straight binary encoding. So when a decimal number is represented by its equivalent binary number, we call it straight binary coding. So in a digital system, we have some form of binary number system. And then we have the external world where we have decimal for the most part. And we're going to be having a constant conversion back and forth between the binary number system and the decimal number system. Now we've shown in the past that if we have a really large decimal number, it gets quite complicated to convert that into binary. So if we can come up with another number system that takes some of the binary number system and the decimal number system and combines it, maybe we can come up with a number system that will help this conversion process and make it easier from a human standpoint to be able to convert it, and also a hardware standpoint. And the system that will help this is the binary coded decimal system, or BCD code. And let's take a look at that. So instead of the straight binary code, what BCD code does is it converts each individual decimal digit to its binary equivalent. So 8, 6, 5, this would be 0, 1, 0, 1. The 6 would be 0, 1, 1, 0. And the 8 would be 1, 0, 0, 0. This is the binary coded decimal form of that decimal number. So the binary coded decimal code only has to be concerned with the decimal numbers 0 through 9. But because we're going to 9, we need 4 places. So we need a 4-bit binary number. So the BCD numbers, of course, will be 0, 0, 0, 0, all the way down to 1, 0, 0, 1. So 0, 0, 0, 1. So these are the valid code groups, 0 through 9 in the BCD code. These are valid. But since we have a 4-bit code group, we can actually count up to 15, but the remaining code groups are invalid. They are not used in the BCD system, since we only have to represent each individual decimal digit in each individual position, 0 through 9. So these code groups are invalid. 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So it should be 6. 1, 2, 3, 4, 5, and 6. These are invalid. So these aren't used. If one of these comes up in a BCD system, you know you have an error, because you should not be seeing any of these code groups. So to reiterate, when each digit of a decimal number is represented by its binary equivalent, this produces a code called the binary coded decimal, or BCD for short. Now, if you compare straight binary code to BCD code, you will notice that BCD code requires more binary bits. And that's because it's less efficient, because it does not use all of the 4-bit binary code groups that it can with a 4-bit number. So it's less efficient, but it's easier to convert, and it's also easier to implement hardware-wise. Now, if you compare the straight binary code for this number 865 decimal, you'll notice it requires 10 bits, where the BCD code, BCD, requires 12 bits. So it's less efficient because we don't use all of the 4-bit code groups available with a 4-bit code. It's less efficient, but it's simpler for the conversion process, and it's easier to implement with hardware. So where will we find BCD code? Well, whenever there's digital inputs and outputs, or digital displays, we got calculators, multimeters, frequency counters. Wherever we have digital displays, or we're inputting decimal information and outputting decimal information, we can use the binary coded decimal system. Now remember, we have 6 code groups that are forbidden in the BCD system. So if you have some hardware using the binary coded decimal system and you come across any of these code groups, you know that you'll have an error, because you should not be using these code groups in the BCD system. Now, you can do mathematical operations with the binary coded decimal system, but you won't be using that in like a modern day computer or microprocessor doing calculations, because it takes more bits to represent a decimal number in BCD. It's just less efficient because it takes more bits. It's going to take more memory space, and it's also harder to implement hardware-wise. It's not as easy as implementing the mathematical operations in binary with hardware. It's more complicated. So you'll find this, like I said, in calculators, multimeters, slower devices where speed is not as critical for display purposes. Speed is not as critical as when mathematical operations and number crunching are being performed in a microprocessor. So let's take a look at we'll just look at the operation of addition using the BCD code. So when adding 2 binary coded decimal numbers, there's 2 possibilities that can occur for any given bit position, and that is that the sum is going to be less than or equal to 9, or the sum is going to be greater than 9. Now, what happens when the sum for any given bit position is going to be greater than 9? Remember that there are 6 4-bit code groups that we can't use, which is 1010, 1011, 1100, 1101, 1110, 1111, 1, 2, 3, 4, 5, 6. So we have to come up with a way of getting the correct sum without using these forbidden 4-bit code groups. So here are 2 examples that will show how to add when any of the bit positions, the sum is going to be equal to, well, it's going to be less than or equal to 9. So this one's pretty straightforward. This here is 0, 1, 0, 1, and the 4 represented in binary coded decimal is 0, 1, 0, 0. We add this together, we have 0, 1, 0, carry the 1, and that equals 9. Right? So this is within the binary coded decimal codes that are allowed. For this one here, we have to break this into the individual binary coded decimals. So this is 0, 1, 0, 0 for the 4. The 5 is 0, 1, 0, 1. The 3 is 0, 0, 1, 1. And the 3 again, 0, 1, 1. So if we add these up, we got 0, carry the 1, 0, and 1. And this is 1, 1, 1, 0. So here we have 8. And here we have 7. So we have 8 and we have 7. So those check out. So you can see here we didn't run into any problems because the results in either of these positions was less than or equal to 9. The problem occurs when the sum is greater than 9. So if we add 6 and 7, we will end up with a result greater than 9. So we have 0, 1, 1, 0. And we have 7, which is 0, 1, 1, 1. So this is 1, 0. That's a 1, carry the 1. And you can see here, that is one of the forbidden code groups. That's 13. That's correct in straight binary, but we're using binary coded decimal system. That is not allowed. So the way this is resolved is because we have 6 code groups that we do not use, we have to skip over those. So we have to add 6 to account for the 6 4-bit code groups that are not allowed. So if we add 6 to this, 0, 1, 1, 0, this is a 1, 1, 0, carry the 1, 0, 1. Remember, we have to account for 4, has to be 4-bit code groups. So here we have 1, and this here is 3. So here we have 13 in BCD. So this is the proper code now for BCD. This is a acceptable code group, and this is also one of the allowed code groups. Of course, it's only one. So whenever the result is greater than 9, we have to add 6 to it. We have to add 6. So 0, 1, 1, 0 gets added to that position to get us to the proper BCD code. So let's do another example. We'll add 47 and 35. So this is 0, 1, 0, 0. This is 0, 1, 1, 1. We have 0, 0, 1, 1. And we have 0, 1, 0, 1. So now we add these together. We have 0, 1, and that's 1. And this is 1, 1, 1, 0. Well, this is an invalid. This is invalid. This is one of the invalid code groups. So let's write down those invalid groups real quick. Invalid. We have 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So this is an invalid group. So we have to add 6 to it. So we have 0, 1, 1, 0. That's 0, 1, 0, carry the 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 1. So now we have 2, and here we have 8. So this is a 2, carry the 1, and we have 8. So here we have the right code groups for the 2 positions in BCD. So whenever the result causes you to get into one of these forbidden code groups, which is greater than 9, you need to add a 6 to jump over those 6 forbidden code groups, invalid code groups, and then you end up with the right result. So you can see the math, even just the addition process, is more complicated with BCD addition than for binary addition. Now remember, one of the benefits of the BCD code is the ease of conversion into the decimal world, or for display purposes. Let's look at a quick example of a circuit that uses BCD code to drive a 7-segment LED display to show a decimal number. So here's the circuit that I built on the Heathkit Digital Trainer breadboard. I have the 4 switches that will allow me to enter in the 4-bit BCD code group 0 through 9, and those will be inputs to this 7447, which is a BCD to 7-segment display decoder driver. So it will decode the BCD code group into outputs that will correspond to the correct LED being activated to produce a corresponding decimal symbol or decimal number 0 through 9 that corresponds to the BCD code. So this chip is an active low, meaning the outputs are normally high, and this is a common anode LED display. So if any of these cathodes are high, and I have the 5 volts on the anode, the LED will not light. The cathode has to be negative with respect to the anode for the LED to be properly biased and to turn on. So in essence, there are 7 individual LEDs in here, and when you light them up in the correct pattern, they'll produce the decimal symbols 0 through 9. So the chip has active lows. So when they go low, corresponding to these BCD inputs, they will light up the individual LEDs here to form the decimal symbol. So if we take a closer look, so the circuit sort of by default is already going to display the decimal 0 because your code group, BCD code, starts off at 0. So you already have 6 individual LEDs lit right here. So to turn them all off, I have to actually apply an invalid BCD code group. So we have all 1s, which is invalid BCD because it's 15, but that will force all these LEDs to be off. So you can see here that we have none of the LEDs are lit on the 7-segment display, and we have highs on all the cathodes. So the outputs from the 7447 are all high, but as soon as we go low, it produces the output required for the LEDs to light to give us the pattern or the symbol for 0. So it decodes the BCD input code to produce the output code to light the proper sequence of LEDs. So if we look at the TTL data book real quick for the 7447, you can see there BCD to 7-segment decoder driver. This chip you can directly drive. You don't have to have any circuitry in between your LCD, your 7-segment display, and the chip. It can directly drive, supply enough current to drive a 7-segment display. So here's how they letter each individual segment, and then you light them up in the proper order to get all your symbols here. And there's the truth table for the output. Now remember, it says on, but that actually is an active low to turn on A, B, C, D, E, F, or G to get that proper number lit. So we can step through the BCD code. We're already at 0. There's 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if I go further in this progression, they're invalid code groups, and you get symbols that are not the decimals 0 through 9. Maybe if I put this sideways, you can see that better. You get a close up. So here are the codes. It's 0, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that about covers the binary coded decimal. The difference between the binary coded decimal and regular binary conversion is that each individual decimal digit is converted to its equivalent straight binary number. So you have 0 through 9. It's less efficient. It takes more bits to represent a decimal number, but it's easier to convert, and it's easier to use hardware-wise also to be able to drive displays, or whenever you're using or having to input or output decimal information. So if you found this video interesting and helpful, don't forget to subscribe, give me a thumbs up, leave a comment, and thanks for watching.